This talk is going to be a little bit more of physics and phenomenological applications of several of the subjects that we have here in the previous talks, in particular on how to address the gravitational two-body problem. So differential equations of Hoyne type, they are good to describe the dynamics of systems involving objects, extended objects rather than point-like objects, like hypergeometric equations. And hopefully today we'll learn a little bit of some properties of this binary black hole problem by studying a little bit the solutions of confluent Hoyne equations in the case of astrophysical black holes. So this talk is going to be based in a few papers that I've written. So probably the most relevant to this discussion is the one that I wrote with Giulio Bonelli, Alessandro Tanzini, and Cristoforo Josa and Xian Su on how to find connections of the differential equations appearing from black hole perturbation theory to the Nekrasov belief function that we have heard today, and then some papers related to the explicit application of this connection formula in the computation of observables for the binary black hole problem. So either thinking of them as point particles or keeping the extended nature of these objects, and you can find more details in these last couple of papers about that. So this is the plan of the talk. So I'm going to start with a small motivation of why we are interested to study solutions for confluent Hoyne differential equation in the context of black hole perturbation theory. And then I'm going to review exactly how these differential equations appear when you do perturbations of the Kerr black holes. So we have seen the explicit form of this differential equation, but we haven't really seen what is the physics behind how these differential equations appear. And once we understand how these differential equations look like and how to connect them to confluent Hoyne differential equations, then we are going to study a little bit the solutions of those differential equations in the context of scattering amplitudes, and in particular then use those scattering amplitudes as building blocks to compute observables in the binary black hole problem. So let me start with this slide, which I took from Thibault's slides at some point. So let me start with this motivation. So what we have in mind is the binary black hole problem, and right now we have a synergy of methods to start to approach this problem. We have post-Newtonian, post-Minkowskian method, gravitational self-force, numerical relativity, and as we transition from the observational to the precision frontier in measurement gravitational wave observations, we are going to have to model. To find models of binary black hole systems as accurate as possible, and to model those, we in particular need to keep as much information as possible about the binary black hole system to do data analysis, but also they should be fast to evaluate. So in the future we're going to have like many events that will require the evaluation of gravitational wave templates very fast. So it's better if you have like semi-analytical results for doing that. But also, we would like to try to understand a little bit more, the solutions of black hole perturbation theory equations. So maybe from a different perspective to the usual general relativity perspective, which is emerging in the recent years, using the language of quantum field theory, and maybe try to find for hidden structure that you wouldn't see if you approach the binary black hole problems in the usual general relativity approach. So the binary black hole problem is mapped into a scattering problem. You think of the bodies of some kind of point-like objects, exchanging graviton between them, and then possibly radiating gravitons that you can eventually measure in a gravitational wave observatory, and to compute observables in this scattering process, there is a well-known prescription for doing now that goes by the name of the Kosower, maybe, and O'Connell formalism. And basically, the formalism tells that if you want to compute how much an observable change in this scattering process, then you need to know two things about the system itself. So first of all, you need to know the initial state of your system, And second of all, you need to know how to write the unitarity evolution of that system. And writing the unitarity evolution of that system means that you have a theory to do explicit computations of observables in this binary system. So in particular, if these objects are very far from each other, you can model them as point particle and think of them as actual point particle minimal coupling to scalars. But eventually, as these objects get closer and closer, they are going to exchange gravitational wave with a high enough energy that they are going to be able to prove the extended nature of these objects themselves. So you need to enlarge your sort of minimal coupling action by some non-minimal coupling operators in your effective theory, which I sort of write in this schematic format as the derivatives, with some free coefficients that are going to have information about the extended nature of the object itself. So you can have information about how you tidally deform these objects, how if part of the energy carried by this exchange wave is absorbed into the graviton, should have information about dissipative effects. Or if some quasi-normal modes are excited in the process, it should have information about that. So it's a very difficult problem, and in particular, it's very difficult to find all of these free coefficients, say for a generic order in the so-called post-Minkowskian expansion, but you can do it order by order in perturbation theory. And once you have studied the scattering process, then you can go back to the bounded orbit case with some analytic continuation prescription. I'm not going to talk too much about that, but there is a few prescriptions that you can find, like EOB Hamiltonian continuation or mapping directly the observables computed in the scattering process to observables computed in the bounded orbit case by the map provided by Gregor and Rafael in 2010. So the important thing from this prescription basically is that there is some sort of separation of a scale that you can use to compute observables order by order in some perturbative parameter. And also, since this is a scattering process, you can use the tools that you use for quantum field theory computations to build higher order observable from lower order, say 3-level like building blocks. So the question for describing the scattering involving extended objects like Kerr black hole is basically, how do you obtain these building blocks, so 3-level building blocks that have information about the black hole itself and not any other kind of objects. So we're gonna try to build these objects from the studying perturbations of the Kerr black hole. So this is the main object of the talk. So basically, we're going to have a Kerr black hole, and we're going to perturb it with some, say, plane wave. This plane wave is going to be scattered due to the gravitational potential created by this black hole. And if you study the asymptotic solutions of this perturbation, you can connect directly to observables defined at Fisher null infinity, such as scattering amplitudes, which are going to be the building blocks to compute two-body observables in our binary black hole problem. So that basically means that we are going to be able to fix some kind of theory, and from that theory you can compute observables, say like scattering angles, or if you have a spin, you can have precession frequencies or redshift, tidal deformabilities of the objects, or in the case where there is absorption, you can compute how much the mass of the angular momentum of a black hole can change, has changed. And a low enough orders in perturbation theory, this guy enters into those observables through this triangle diagram. So it's composed of this quantum amplitude that we are going to try to understand how to extract from the solutions of the Tucholsky equation. So a first approach to do black hole perturbation theory, you have your black hole spacetime, and then you introduce a small perturbation of that black hole. And the idea will be, to try to study the evolution of that small perturbation in that spacetime background. So basically, you could sort of expand your metric as the black hole background plus some small perturbation, and find through the the Einstein equation for the system, find like some kind of differential equation that describes how this perturbation evolves. And this was the first kind of approach used back in the 50s by Reggie Wheeler and Cyril Lee to find a differential equation for the different components for the perturbations of the Schwarzschild black hole, and find a differential equation that admits separation of variables. That differential equation is of complement-Hom type, but since we are interested in study, say also spin effects, you will say, okay, can you do the same approach? Do like metric perturbations of, say, the Schwarzschild, the Kerr black hole. That's something that is very difficult to do in this formalism, because there is not much symmetries in the system, and I am not aware that people have actually gotten differential equation, metric perturbation equations for the Kerr black hole. So instead, the solution to try to find perturbations of the Kerr black hole was given back in the 70s by Tukhowsky, in which instead of thinking of perturbations of the space-time of the metric, you think of perturbations of the curvature perturbations. So basically, the Weyl scalars, in particular, psi0 and psi4, which are the ones that are that decrease not as fast as infinity, which are the ones that allows us to compute a scattering amplitude from looking at perturbations of these objects. And then if you are interested in finding the metric perturbations, you can sort of reconstruct them from these scalars.
Sorry, but are these enough to reconstruct the full metric perturbations?
Probably at least at infinity, yes. Because these are the ones that survive, that don't decay too fast at infinity.
Ah, okay, so the response at infinity.
Yeah. So, what is the Newman-Penrose formalism? So, the Newman-Penrose formalism is some special type of tetrad formalism. So, tetrad formalism is basically, like you have your background space-time, and then at every point in the space-time, you define a tetrad, local frame where you can do computation around this point. So you can map space-time indices for any tensor to tetrad indices, and in particular, you can have 4 vectors in that tetrad. And if you choose, for instance, orthonormal tetrad vectors, the tetrad metric around this point would be diagonal and constant. But in general, it doesn't have to be. You don't have to choose an orthonormal basis. So you can use a basis which is not orthonormal, and the tetrad metric can change. So the idea is then to try to do general relativity, not in coordinate indices mu, but in tetrad indices A, B, C, and so on and so forth. So in particular, if you want to study, the Einstein's equation, you also need to know how to take derivatives in the tetrad metric. So taking derivatives in the tetrad metric is some sort of simple. So by the observation that these covariant tetrad vectors, they define directional derivatives. So for instance, if you want to apply the tetrad derivative of a scalar function, is just taking the usual partial derivative of the scalar function and then projecting this index with the tetrad vector. You can do the same also with derivatives of space-time vectors and space-time fields. But the difference with the scalar one is that now you're going to have to take the covariant derivative here, and also you're going to have some connection coefficients. So these connection coefficients, rotation coefficients, are given by this. You take one derivative of one of the tetrad fields, and then you project the remaining 2 space-time indices with these 2 tetrad vectors. So two things to remember. One, that these covariant tetrad vectors define derivatives, and 2, that you have the connection coefficients in terms of those tetrad vectors. And Newman-Penrose formalism is choosing a special type of tetrad define perturbations in this special type of tetrad. So you have your 4 tetrad vectors are going to be 2 reals, L and M, and then 2 complex, M and M bar. So M bar is the complex conjugate of M, and actually, if you think of scattering amplitudes, this M and M bar, the asymptotic form of those ones should be sort of identified with polarization vectors in your scattering amplitudes. So the space-time metric, you can reconstruct it in this symmetrized way. And in this Newman-Penrose formalism, the derivatives, they take spatial names like D, capital delta, or small delta star. And the same, the Ricci rotation coefficients, the ones that are non-zero, they take also these special names. So if you look at the original paper by Tukolsky, for instance, you see all of these symbols. It's nothing just but the directional derivatives and the rotation coefficients. Okay, so once you have defined the tetrad in the Newman-Penrose formalism, then you can use that tetrad to compute, say, for instance, the 10 independent components of the Weyl tensor. So if you are interested to doing spin 2 perturbations of the Kerr black hole, you're going to have to do to compute the components of the Weyl tensor. And these are given by different projections of the space-time indices with different values of the tetrad. In particular, the ones that we're going to be interested in are psi 0 and psi 4, as I was telling you. And then doing perturbations of your background space-time, that basically means, to do perturbations of your tetrad vectors. So you have some background tetrad vector LA, and then you perturb it with some small tetrad vectors LV, and you want to find the differential equation that this perturbation satisfies. So if you keep the leading order in epsilon, all of the Newman-Penrose quantities, you're going to be able to expand as some background plus some perturbation. In particular, the radiation scalar is going to have like a background part and a perturbation part, which we want to solve for. So this tetrad formalism is very, very generic. So far, I haven't really said that this has. I just took a generic background spacetime, and then you can try to use it to write differential equations for an explicit example of spacetime. So, for instance, back in the 70s, this idea was used to try to compute the differential equations for the Schwarzschild black hole by Barden and Press. Of course, they give you the same information as the differential equation that Reggie Wheeler gives you, right? So you can transform between the Reggie Wheeler and these guys. But the one that we are interested in this talk are really the breakthrough of the Tukolsky equation, which was finding a differential equation for certain decoupled components of the Weyl tensor, in particular psi 0 and psi 4, which will admit separation of variables. So this differential equation for psi 0 and psi 4 are these guys, and actually this differential equation is not only for the Kerr black hole, is for generic Petrov type D spacetime, where you can set to 0 some of the Weyl scalar for the background metric and some of the connection coefficients. And this is also so far coordinate independent, right? So you haven't really chosen any reference frame to evaluate this differential equation. So to find an explicit differential equation, for instance, you have to choose a coordinate system. And for instance, you can choose the coordinate system given by the Boyer-Lindquist coordinates, in which the tetrad vectors are these guys. So R is like a radial coordinate, A is like the rotation parameter of the Kerr black hole, which is basically the angular momentum per unit mass of the Kerr black hole. And then an M is the mass, and then the symbols are the different delta and sigma symbols are related to those guys. So theta and phi are going to be like two directions in the celestial sphere. And once you write your directional derivatives and connection coefficients for this special tetrad, you find the so-called Tykowski master equations. So, so this is actually the equation for generic type of perturbation. So I was describing how to obtain spin 2 perturbations of the Kerr black hole, right? You send sort of like a gravitational wave, and then it perturbs the black hole. But actually, you can send other type of waves, like scalar wave or photon wave. And the differential equation looks very much the same. Instead of having 2 as the parameter for gravitational wave, you're going to have a generic spin parameter for different type of perturbations of the Kerr black hole. So this is a partial differential equation, which still doesn't seem too much of the differential equation that we have heard throughout the couple of talks in this morning. So for related to those differential equations, you have to write the separation of variables for the Tykowski scalar. So you can write an angular function capturing the angular dependence, and some radial function capturing the radial dependence. And it turns out these two functions admit separate differential equations. And thus the differential equation can be separated thanks to the existence of this very magic separation constant. And the way in which you have to think of this separation constant is simply like the wavy analog of the Carter constant. So if you are computing geodesics in the Kerr background, you know that these geodesics are integrable because of the existence of this Carter constant. So the separation of variables in the Tykowski equation is also possible due to the existence of these separation constants, which I'm writing as an expansion in powers of A, the spin of the black hole, and omega, which is somehow like the energy that of the wave perturbing the black hole. So this differential equation is of Hoyne type, and actually for Kerr black holes is of confluent Hoyne type. There is a generic, if you are perturbing generic type D metrics, they are differential equations of certain Hoyne type. We are interested in the solutions for the Kerr black hole, which are the solutions, the differential equations of confluent Hoyne type. That means basically that you can put, say, this radial and this angular differential equations in some kind of a Schrodinger kind of equation. So you can find a dictionary that maps the parameters in these gravitational perturbation equations to the parameters in the normal Hoyne differential equation or the confluent Hoyne differential equation. So that's great. So the message so far is that if you are perturbing black holes, you end up with differential equations of confluent Hoyne type, and we know how to relate those confluent Hoyne solutions of those confluent Hoyne equations to these gauge theory objects like the Nekrasov successibility functions or the conformal blocks that Alessandro was telling us. So that means that in terms of the connection problem, you are going to find explicit form for the connection coefficients. And a more physical way of thinking of this connection problem is like you impose some boundary conditions in some regions. Let's say if you are imposing boundary condition near the horizon of the black hole, and then the information about this boundary condition in the near region is going to be transferred towards, say, the far region, say at infinity, through those connection formulas. So basically, by asking that the solutions in the near zone and the far zone they overlap somewhere in the intermediate region, and that's actually the approach that the Manu, Suzuki, and Takasugi took for writing solutions of the confluent Hoyne equation was expanding the radial solutions in terms of either hypergeometrics or column functions, and then asking for this solution to be to overlap somewhere in the intermediate region, and in that way you can find some recursion relation that these coefficients have to satisfy order by order in the say a small frequency expansion, for instance. So once you solve the connection problem, then you can ask, what is the asymptotic form of this solution? So in particular, what is the asymptotic form of the radial solution as you approach, say, infinity? Because from that asymptotic form, you can define observables, which are going to be our scattering amplitude. So basically, you're going to have at infinity a superposition of two terms, an incoming and a reflected wave. And the connection formula gives us an explicit relation for the ratio of these incoming and reflected coefficients. So we're going to see how they look like in terms of the Nekrasov-Chakraborty function. But by having this connection formula, then you can define scattering amplitude at every angle on the Celestian sphere by just doing an infinite sum of partial waves. So what we have in here are the solutions to the angular problem, the so-called spin-weighted spheroidal harmonics, and there is no closed solution for this one either, because these are solutions of the Confling-Hoyne equation as well, and then the asymptotic solution for the radial equation. So this is what the solution of the connection formula, connection probably will look like in terms of the Nekrasov-Chakraborty function. So we were hearing from Alessandro that there is like two channels in which can contribute to the conformal Bloch expansion. So roughly speaking, there is one channel which gets activated once the energy of the gravitational wave is big enough to start proving the nature of the black hole horizon. That's what we call the near-zone solution. And then there is another piece which does not activate for low, there's a piece that only survives in the low frequency limit, which we call the far zone solution, which is given by this red piece. And the objects entering in these formulas, the important ones are this exponential, which is in the exponential we have the Nekrasov-Chakraborty function, a function of these masses and A and lambda parameters. The near zone solution is also a function of this kappa, which is the so-called tidal response function, and has information about how the black hole itself gets, tidal is disrupted or can absorb energy down the horizon. And then there is the dictionary that maps the black hole perturbation theory parameters, say like a post-Minkowskian-like parameter, gm omega, divided by the energy, the wavelength of the perturbing wave, and then S is the spin of the perturbations, can be gravitational, electromagnetic, and so on and so forth. And this is the coupling constant in the gauge theory, which is roughly speaking proportional to epsilon. So in this sort of more astrophysical language, this expansion in the gauge theory parameter, you can understand it as some kind of post-Minkowskian expansion when you are doing black hole perturbation theory. So important to remember, you have like some kind of horizon parameter, this kappa, which is the square root minus chi squared, where chi is this spinless, dimensionless spin parameter of the curved black hole. And to get an actual horizon of the black hole, you need to keep that guy smaller or equal to 1. So let me tell you a little bit about these solutions, because a very nice thing about writing the connection formula in terms of the Nekrasov-Chakraborty function is that even though you don't know the explicit form for this function, you know some of the symmetries of this function, and some of those symmetries allows you to prove certain things that you will hardly have ever will have not been able to prove in other approaches, like say the MST approach. So the first thing that you can prove using the symmetries of the of the Nekrasov-Chakraborty function is that this far zone sort of describes the zone in which you can think of the black hole as a point particle, and the phase shift for the far zone is purely conservative. That means that no energy is going down the horizon of the black hole. So all of the energy that comes in will go out. And very nicely, the horizon parameter kappa never appears in this far zone contribution, and that aligns very nicely with, say, some spin multiple expansion for the for the Kerr black hole itself. And then in terms of resummation, as we were hearing from Alba, this Nekrasov function allows you to do different kind of resummation. In particular, you can show that this sum of MST coefficients, what nu is the so-called renormalized angular momentum, it becomes this very nice exponential. And the reason, roughly speaking, is because this MST coefficient scale like GM omega, so these sum are roughly speaking like a PM expansion of this exponential. So that's very nice. So now for the near zone, in the near zone you have this bunch of gamma functions that we saw in Alessandra's talk. In particular, these gamma functions are this product of gamma functions is symmetric in the three gauge masses in the gauge theory, and there is also the appearance of another resummation of the MST, certain combination of MST coefficients in this derivative of the Nekrasov function. So this tidal response function is non-analytic in G, unlike the far zone contribution, which are analytic in G, and there is both conservative and dissipative effects encapsulated in this tidal response function. So absorption is contained in this modulus of this factor in the far zone and near zone solution, and also if you want to study the quasi-normal mode spectrum of the black hole, well, you just have to remember that the quasi-normal modes are given by the poles of the scattering amplitude. So in particular, you can find a very nice quantization condition for the quasi-normal mode by asking this guy here to vanish. So and this quasi-normal mode quantization condition actually this resumes into this nice exponential, which you have the one loop plus instanton corrections.
Is it really non-analytic in G? I thought this is supposed to be captured by local operators in the worksheet with power counting, which is just powers of G. Like, where is the non-analytic?
Well, yeah, there is a log GM omega, right? So the reason is because this A, which is like the renormalized angular momentum, receive G contributions, right? So you have a GM omega to the GM omega expansion will give you those log of G omegas, right? So something interesting about these near zone solutions is that you can make them vanish in two ways. So one way in which you can make them vanish is by taking the static limit. So the reason is that this scale is proportional to G itself. So you can kill this guy in the omega goes to 0 limit. And in this limit, the Confluent-Hoyne equation just becomes a hypergeometric equation. And roughly speaking, the solution, the problem becomes just like the scattering of a wave of something that is point-like. And then there is another way in which you can make this guy vanish, which is in the near extremal and near superradian. So if this is near extremal, since this guy is proportional to kappa itself, in the near extremal limit, this guy vanishes, so this kappa goes to 0 as well. But you have to make it also near superradian, because this M1 will diverge in the near extremal limit, so you also have to tune the frequency of the wave to correspond to the near superradian threshold in such a way that you don't get anything that explodes. So and there is a very nice paper that appeared this week on the archive telling the story about this limit in which a nice conformal symmetry arises in the near extremal near superradian regime. So as we were hearing from Alessandro, there is many other kind of black hole and some more exotic objects for which you can write black hole differential equations of certain Hoyne type or certain other yes, let's say Hond type of its generalization, and there is, this goes now by the name of the quasi-normal modes gauge theory correspondence. We're going to stick to the Kerr black hole, but I just want to mention this for completeness. Connection also with this confluent diagram that Alessandro was showing us. So okay, so we have the solutions of the Hond differential equations in terms of this Nekrasov-Chotanishvili function, and in principle we can now compute scattering amplitudes, right? Objects that are defined at infinity, right? So I was telling you that the way to do that, to compute the scattering amplitudes, taking this ratio of coefficients coming from the connection formula, and then doing this infinite sum of like partial waves. But this is a very difficult problem to do in general. Well, on the one hand, because you don't know explicit expression to all orders in perturbation theory of this connection formula. And on the other hand, you also don't know what are all orders in spin multiple expansion form for these spin-weighted spheroidal harmonics. And also, these are some which are not very easy to do. They can be done in certain limits, but the best you can do is try to write like an ansatz for what these sums look like, and try to match that ansatz on mode by mode. So in particular, if we want to use this object to compute observables in the binary black hole problem, we would like to try to extract a piece that looks like a tree-level amplitude. And that you can do very easily. So you can define like something that looks like a tree level by combining solutions that from the far zone and solution from the near zone that look like contact objects in general. So a Lie ordering perturbation theory, meaning in the post-Minkowskian expansion G and omega, you have some far zone solution, then the Lie L equals 2 solution from the near zone. And in a covariant form, the far zone solutions, they up to say 4th order in spin multiple expansion. When you expand this exponential up to 4th order, they are given exactly by the far zone solutions, where you can think of the black hole as some kind of minimal spinning point particle coupling in a minimal way to gravity. But this scattering amplitude itself is a little bit sick because there is some hidden poles in this W vector that I'm not writing explicitly that they cancel with these zeros of the encoded in the scalar amplitude. And to remove those unphysical poles, you need to start introducing contact terms order by order in the spin multiple expansion. So those contact terms start to appear at first for the gravitational case at 4th order in spin multiple expansion. Actually, you can show that the deformations at spin to the 4th, they are of Love type, meaning that they are actually quadratic either in the electric or magnetic component of the Riemann Riemann tensor, and by matching the solutions of the Tykowski equation, the Tykowski equation tells you that only this exponential is the form starting at spin to the 5th. So that means that at spin to the 4th, all of the coefficients, they have to vanish. And that's like an on-shell manifestation of the vanishing of the Love numbers, at least in this sort of perturbative approach. Higher orders in spin, in general, you can write some deformation. This set is some quadratic combination of spin multiple operators. And these coefficients you can get from solutions of the Tykowski equation.
Can you? Then you need to compute loops in RFT?
Yes.
Okay, but so no one has done that?
No. So I was coming to that. Exactly. So in principle, you can sort of package all of this in some ansatz for what this object like, and you can match what this object looks like in the UE computation. But of course, you're going to have to relate those guys to a theory. In particular, these log guys that we're talking about that are non-analytic. You have to relate to the running of some Love numbers. So that's for the.
So you are saying to compute Love numbers, you need to know the Love numbers? You
No.
said the Wilson coefficients are not.
Okay, here these are not Wilson coefficients. These are just whatever the Tukolsky solution give me, the UV solution. And now I can write an effective field theory to compute this an scattering amplitude that looks like this. Then I can match those two results, and the matching condition will tell me that the effective coefficient that you write in your effective field theory are going to have some running, right? So Julio and Zihan did this in the case in which you were considering scalar perturbations of a Schwarzschild black hole, but this generated to Kerr as well, generalized to Kerr as well. So today I want to talk about a little bit about a sector that is not addressed very much in this community, which is the absorptive sector, because it comes up very high order in the post-Minkowskian expansion, but nevertheless you can have solutions you can have explicit solutions from looking at the connection solution to the Tukolsky equation. So in particular, this eta, which is like the absorption factor in the near sum solutions of the Tukolsky equation, it has this post-Minkowskian scaling, meaning it starts contribute at say if you are dealing with the spin 2 perturbation, it start contributed at order epsilon to the fifth. So very high order in the post-Minkowskian expansion, but you can capture those in the Tukolsky solution. And in particular, you can find an explicit covariant form for this leading L equals 2 contribution in terms of a contact term. And that's sort of resonate with the idea that dissipative effects are somehow captured by localized degrees of freedom on the word line. So that's very the amplitude's way of putting that statement. And I'm going to use this guy and the equivalent for a Schwarzschild black hole to compute absorptive observables in the binary black hole problem as an application to explicit solutions to these differential equations in leading order in the post-Minkowskian expansion. So what I'm going to consider some black hole which is moving in the space-time, some gravitational background created by say other black hole. And I'm going to allow my black hole to move, say, at relativistic velocities if it wants. Why not? And I want to ask, due to the existence of these absorptive effects encoding the Tukolsky solution, by how much the mass of this black hole will change a leading order in the post-Minkowskian expansion. So basically, the leading order in which this ratio between the size of the black hole and the curvature of the background is start to contribute for the first time. And for this talk, I'm going to specialize to the aligned spin limit, meaning the limit in which the spin of the black hole is aligned with the total angular momentum of the system. So to compute that, well, we use the K-MOC formalism. It's a very easy computation. So the change in mass of the black hole is roughly speaking given by the expectation value of the energy carried by these gravitons that is absorbed into the black hole. And that absorptive contribution is captured by the absorptive contribution in the elastic scattering amplitude. So the absorptive quantum amplitude that I extracted at order epsilon to the fifth from black hole perturbation theory and higher orders in G if I want. So if my black hole is a Schwarzschild black hole moving in background, gravitational background created by another black hole, say, the mass of this Schwarzschild black hole starts to change at 7 order in the Newton's coupling. So that's very, very high post-Minkowskian order and presumably not observable by a gravitational wave observatory. If you were doing bounded orbit system, that would be like a 4 post-Newtonian contribution on top of the leading quadrupole contribution. But here I'm doing a scattering, so I'm keeping the velocity of the black hole to be in general relativistic with this Lorentz factor. For Kerr, on the other hand, you can use this scattering amplitude, the absorptive contribution to scattering amplitude, to compute how much the mass of the Kerr black hole will change. And you see that it has some kind of PM enhancement because it has one lower order in the Newton's constant due to the existence of the spin. So that is to say, if you take the spin parameter of the Kerr black hole to go to 0, this guy goes to zero instead of going to the Schwarzschild result. So that's a discontinuous limit. And this we know from work by Poisson in 2004. So the question is, how do you recover the actual Schwarzschild result from the spinless limit of the Kerr black hole? Well, what you have to do is just, instead of putting the leading contribution to the absorptive contour amplitude for Kerr black hole, epsilon to the 5, you're going to have to put the contribution epsilon to the 6. And that's something very easy to do. So this is the result of that loop integral. So these coefficients are related to the coefficients of this triangle integral. They have this relativistic factor. But something important is that these guys, they have different powers of G that add up to the 7 powers of G that you first observe in the Schwarzschild black hole. And all of these C coefficients you get from the explicit solutions of the Tykowski equation next to Lee in order in the PM expansion for a spinning black hole. So in particular, you see that this expression goes with 5th powers of the spinless parameter of the Kerr black hole. And these coefficients, they also come with 5th powers of the spinless parameter of the Kerr black hole. So that will give you, from some of these terms, that will give you something that scales like spin to the 0. And naively, you will say, okay, maybe the only contribution is this guy, this constant guy. But actually, it turns out that if you put only this contribution, you will get something that does not give you exactly a Schwarzschild black hole. You have also take the spinless, the chi goes to 0 limit of this hypergeometric function. So in the chi goes to 0 limit, this function scales like 1 over chi that cancels some of this chi here and give you something that contributes to the Schwarzschild limit. So the main message basically is that in order to recover observable for the Schwarzschild black hole, you need to keep these non-rational functions of the spin parameter in the solution to the Tykowski equation.
Javier, here this picture is just the cut that you use, but the gravitons are in the radiation region, right? So that, for instance, that matter leg is not on shell, because otherwise.
Yeah. So actually, since this is the imaginary, the absorption contribution, the graviton, the matter line, you cut it.
Sorry, but then those gravitons cannot be on shell, right? By energy conservation. So.
Well, but here you are putting the absorptive contribution. That I think.
No, but on the left-hand side it has to be absorptive. But my point is that if on the right-hand side you cut the matter leg, then you're setting the energy of that graviton to 0, so it cannot go on shell.
Oh, this guy.
So I think it must be not cut. Like you can construct the integrand using that cut, but when you do the integral. That's
a good point. Yeah, it turns out that the coefficient itself is just like you have the cut, but the integral itself is not the cut. You're right. Yeah. Great. So that's cute applications of explicit result for absorptive effects in binary black hole problems, at least in the scattering scenario. And if you want to see applications in the conservative sector, you can check out this paper that we wrote with Mohamed Kali, Matteo Sergalo, Justin Vine, and Chris Kavanagh in the summer this year, which tell you how to include this higher order solution in the spin multiple expansion for the Tykowski equation in the conservative sector of the binary black hole problem. So let me stop in here. So hopefully I give you a glimpse of how to use these solutions to the Tykowski equation to study, to compute observable in the binary black hole problem, at least a few orders in the post-Minkowskian expansion, how to show how to use the solution to model spin effects. I find this formula very interesting because, so far, although I've just explored the solutions, some perturbative form of this solution, this formula itself is a closed form formula. And presumably there is a lot of physics hidden in this formula that we would like to understand. So because basically we have reduced the problem of solving an ordinary differential equation to just solving is now a combinatorics problem. So the question is, are there any hidden symmetries lying in there? Anything more interesting in this formula than just, these nice near and far zone factorizations and getting some insight about the near and far zone solutions? Is there anything that hints, towards some more correspondence between black holes and systems that are not made of black holes? Since, we have mapped a gravitational problem in something that doesn't have anything to do with gravity in principle. So that would be something very interesting to study. So thanks for your attention.
Question. Is this decomposition as the product of far zone and near zone well defined? How is it defined that this is?
Well, what did I do? How can I? Well, I don't know how to go up. Yeah, this decomposition is basically inspired by the MST sort of decomposition of the solutions of the Tukolsky equation in the near zone region and far zone region. It is, the two different contributions, they sort of separate at few lower orders in the perturbation theory because they come from two different channels in the conformal block expansion. So as Alan Sutter was saying, you have two different channels. The far zone solution comes from one channel, and then the near zone solution comes from the energy limit at which the other channel is excited. Say it's a well-defined object in terms of, if you think of these conformal block channels, that if you turn off one of the channels, if you are doing computation in energy in such a way that only one channel is excited, it's fine. But I think in generic, if you are doing computation for generic energies, I'm not sure the separation is well defined. And in particular, because this near and far zone separation will start to show unphysical poles, like say L equals 2 or L equals 3 poles, that will cancel from the near zone and the far zone solution if you combine the two together at sufficient high order in perturbation theory. So I would say it's a well-defined separation in the low energy limit, but in the high energy limit where these say tidal deformations and point particle like contribution mixed together.
Is that if you expand in perturbation theory, you have these poles, but do you have an understanding, like for instance, there will be some pole at L equals 2 with the leading dynamical tide and or something, but do you understand this with some formula? Does it make sense, like the separation, if you try to plug in L before, there's an order of limits thing, right?
And
in small frequency and then plug in the value of the multiple, or do it the other, or just plug in the value of the multiple. Do you know if these objects are well defined separately for generic frequency, or?
I don't know exactly.
If you want to do the analytic continuation, you should take the full formula.
Yes.
Because in that, the pole cancels.
Yeah, I understand that the poles cancel.
So you cannot do it in just one piece. So what Fabian was saying is that the connection formula is telling you after the dictionary what is the perturbation. So at which order of the perturbation the second channel turns up. But if you want to analyze the analytic properties of the connection coefficients, you have to consider everything full. You cannot separate. So this is.
I know that if you consider the whole thing, there's no issues because that's
yes, exactly. Yes, yes.
I was just wondering if, because for instance, for low enough L's, well, we already know that for L equals 0 or L equals 1, these things will be well defined. For L equals 2, we know that there's things that can go wrong.
Okay.
Yeah, so that's precisely the value at which the near zone solution, the sort of finite size properties of the black hole start to show up. We haven't really checked on doing the opposite limit, first taking the L equals 2 and then taking the PM expansion.
Because the second channel enters with it's retarded, so to speak, with L.
Yes.
Yes. So if you have L0, of course, no, you don't have this effect. Yeah.
Yes, but I mean the reason we haven't done it is because we don't know an all-ordered PM solution for the Nekrasov-Chateauvilli function to first take L equals say 2 and then take the PM expansion.
Yeah, but maybe you know that it's analytic problem. I mean, maybe you don't know the explicit expression, but one can figure out if, as a function of L, they make sense.
Yeah, that's something we haven't.
Separate things. Yeah.
That's something we haven't checked.
But also, you know the all-order expression before taking the epsilon to 0 limit. So why don't you use the all-order expression before and then?
Well, you know the all-order expression, but it's like some kind of recursive. Well, you need to know what is the explicit solution for the, say, renormalized angular momentum, right? This a guy, so you can.
You mean like inverting Mattone?
Exactly. You have to invert Mattone relation to all orders in perturbation theory first, in order to be able to say anything about the L equals 2 expansion.
So you can plot that function numerically, right?
Yeah, that's something that's a good idea. We didn't do it so far, but presumably we can start checking that numerically to see what it looks like.
But the MST formalism was suggesting a factorization, no?
Yes, in some sense, yes.
Define in MST, for instance.
Say again, please.
Was the factorization not better defined? It was always okay.
Because they choose these finite size effects, and they're
exactly. So this effect that you started exciting once you include the other channel in the conformal block expansion. So we don't know. We'll have to check.
Questions? If not, let's thank the speaker again.